Section 1. Hey guys, tonight we slip past creaking library shelves dusted with old physics journals, past the gentle ticking of precision clocks in quiet labs, and out into a universe threaded with mysteries Einstein himself once teased apart. Under the glow of his desk lamp, you can practically smell the warm varnish on the wooden furniture, feel the scratch of fountain pen on paper, and hear the faint creak of his chair as he leaned in closer, scrawling equations that would change how we see reality itself. You're about to tiptoe into a world woven from invisible threads, a cosmic fabric so delicate that even your thoughts might tremble to imagine it. And fair warning, you probably won't survive this with your brain entirely intact, because pondering the fabric of spacetime is one of those delightful paths that ends with your mind curled up in a corner, rocking back and forth, whispering Einstein was right over and over again. So, before you get comfortable, take a moment to like the video and subscribe a bit, only if you genuinely enjoy what I do here. And hey, let me know in the comments where you're listening from and what time it is right now. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. So there you are, floating behind Einstein as he rummages through the mess on his desk. Papers everywhere, coffee rings on important notes, a violin leaning precariously against a stack of journals. His hair is a mad swirl of static electricity, and his eyes sparkle with secrets. And in this cluttered space, he's imagining the universe as a kind of woven cloth, a seamless continuum called spacetime. You close your eyes and drift outward, picturing spacetime not as empty darkness, but as something tangible, like silk threads stretched tight across invisible beams. You picture cosmic filaments stretching across the cosmos, vast threads linking clusters of galaxies, forming a sort of delicate lace. It's quiet out here, so quiet it hums in your chest. Let the pause after a violin bow lifts from a string. Mainstream fact? Well, here's a solid one. Einstein's general theory of relativity, published in 1915, replaced Newton's idea of gravity as a force with a vision of spacetime, bending around massive objects. Gravity wasn't just an invisible pull, it was geometry. Spacetime itself warped and curved, which incidentally means that Earth is basically surfing on a flexible cosmic trampoline. You didn't think you were that cool, did you? And while we're rummaging around Einstein's personal trivia drawer, did you know he kept a little compass as a child, and was obsessed with how the needle moved without touching anything? That tiny swirling needle planted the seed that eventually blossomed into his passion for unseen forces shaping the universe. Physicists still argue whether that childhood curiosity truly foreshadowed his revolutionary ideas, or whether it's just one of those poetic stories people love to tell after someone's famous. Either way, it's pretty charming. Back in your mental trip, you watch as starlight pours through the cosmic fabric, like glints of glitter sliding down black silk. The universe doesn't feel empty. It feels alive, stretching, vibrating, sometimes gently quivering under the weight of celestial bodies. The gravity of the sun pulls Earth's spacetime well into a soft depression, like someone leaning gently into a memory foam mattress, and you're the tiny speck rolling around that curve, all while sipping iced coffee and scrolling memes. And speaking of curves, Einstein's equations suggest that even massless particles like photons, particles of light, follow these invisible pathways carved into the cosmic cloth. They don't simply travel in straight lines. They trace the curves and dips and folds of this universal tapestry, which makes you wonder whether the next sunrise you'll see is actually light, following a gently sloped slide through cosmic valleys. But your sunrise never seemed so dramatic, huh? You recall the violin under Einstein's desk, perhaps the same violin he named Lena. He used to say that music helped him think, that sometimes the mathematical beauty of physics felt like music itself. Imagine him, bow in hand, lost in a melody, only to pause mid-phrase, because his brain suddenly cracked open a new insight about how gravity warps time. You're tempted to picture equations floating like musical notes above his head. You chuckle, because somewhere out there, physicists still argue whether Einstein's musical instincts truly guided his physics, or whether he just needed a break from relentless calculations. Either way, the violin's presence somehow makes the cosmic fabric feel more intimate. A soft cosmic breeze whispers through the star fields, And you sense how this fabric isn't just a metaphor. It's measurable. Scientists detect its distortions with astonishing precision, like the recent measurements of starlight bending around the sun during an eclipse, confirming Einstein's predictions. And that's not even getting into gravitational waves, which we'll tiptoe into soon. As you hover there, cradled by starlight and cosmic silk, it's tempting to think of the universe as static, a silent, perfect cloth draped over nothingness. But the truth is, this fabric is alive with tension and motion, expanding, rippling, and occasionally tearing in ways we're only beginning to grasp. So you keep floating, eyes wide, and wonder if the universe is woven, or what is the weaver? And more crucially, where do you fit into the pattern? Of course, you're probably still trying to wrap your head around the fact that you're basically perched on a stretchy trampoline while orbiting a fiery nuclear reactor at 67,000 miles per hour. Fun times. Section 2. You're still hovering there, wrapped in cosmic velvet, when something subtle begins to tremble under your metaphysical feet. It's like standing on a glassy pond and feeling the ripples of a distant pebble, long before you see the splash. That's the quiet beauty hidden inside the fabric of space-time thway. Even the gentlest shiver carries news from unimaginable distances. Tonight, those ripples have a name: gravitational waves. Picture it, to black holes locked in a cosmic tango, spiraling closer and closer until they finally crash into each other. Like heavyweight boxers in the dark, the collision sends ripples radiating outward, stretching and squeezing the very fabric you're floating on. But here's the wild part: these cosmic quakes don't roar like thunder. They slip through spacetime so quietly that it takes instruments more sensitive than anything your five senses can fathom just to detect them. Mainstream fact time. It wasn't until 2015 that scientists at Legat enormous laser observatories in the US directly measured gravitational waves for the first time. Einstein predicted them a century earlier, but even he suspected they'd be too faint to ever detect. Yet there it was, a tiny blip in LIGO's data, the faintest chirp that confirmed two black holes had collided over 1 billion years ago. And here's your quirky Einstein tidbit. While working on general relativity, Einstein sometimes got so absorbed that he'd forget to eat or sleep. Friends reportedly worried he'd waste away into an equation himself. Physicists still argue whether his deep dives into abstract math were fueled purely by genius, or by an impressive amount of caffeine. If you ask me, probably both. Your cosmic perspective zooms outward, and you notice how calm it all appears. Stars glimmer like frost under moonlight. Nebulae bloom in soft swirls of rose and indigo. It's easy to believe space is silent and still. But underneath, those gravitational waves ripple past, altering distances by mere fractions of a proton's width. You'd think something so subtle wouldn't matter. But the waves carry information about the most violent events in the universe: black holes colliding, neutron stars smashing together, entire galaxies shaking loose, secrets older than Earth itself. It's like eavesdropping on cosmic gossip whispered in gravity's secret language. And remember that violin leaning under Einstein's desk? Imagine it now vibrating softly, strings quivering not from a bow, but from gravitational waves drifting through the room. If those waves are passing Earth right now, your body's length is technically expanding and shrinking ever so slightly. Don't worry, it's not enough to squeeze your organs into goo or anything. Which is nice, because nobody wants a bedtime story ending in spontaneous organ goo. But here's a fun question. Physicists still argue whether gravitational waves might one day reveal entirely new physics. Could they expose hidden dimensions, dark matter secrets, or flaws in Einstein's own theory? Or are they merely confirming what we already suspect about cosmic collisions? The debate is as rippled as the waves themselves. As you drift deeper into this cosmic pool, you picture the detectors on Earth, enormous L-shaped tunnels where lasers bounce back and forth, measuring changes in length smaller than a fraction of an atom. It's delightfully absurd, like using a ruler to detect a gnat sneezing 3 galaxies away. Yet somehow, humanity pulled it off. You float over LIGO, peering down at scientists celebrating around computer screens the day they caught that first gravitational chirp. You can't help smiling at the thought of Einstein, wild hair and all, grinning like a kid who's just realized his secret hunch was true. And speaking of ripples, Here's your next mental exercise. If spacetime is a fabric, then gravitational waves are its music. They're the gentle thrumming of a cosmic harp strummed by colliding stars. You picture these waves stretching the distances between planets ever so slightly. A kind of cosmic breathing you'd never notice in your day-to-day hustle of emails and grocery runs. It makes you wonder if we're wrapped in a sea of invisible ripples. How many stories have passed right through us without leaving a trace we can feel? Supernovas exploding, black holes roaring in silent darkness, entire chapters of cosmic drama unfolding in gravitational whispers. And somewhere, Einstein might still be scratching equations on his chalkboard, eyes distant, dreaming of the hidden music playing through the cosmos. It's oddly comforting to know that amid the infinite scale of the universe, there's a human connection, a brilliant mind who first glimpsed the possibility that space itself can ripple like water. You drift in silence, feeling those gentle tremors brushing against your perception like the softest breeze. A breeze that's crossed galaxies, a breeze that carries secrets of cosmic collisions older than Earth's first fish. And as you listen, the cosmic harp keeps strumming its subtle tune, inviting you further into the quiet beauty hidden inside the fabric of spacetime. So yeah, you're currently vibrating in sympathy with the echoes of two black holes smashing together 1 billion years ago. Sleep tight. Section 3. Floating there in the hush between stars, you begin to notice that the cosmic fabric isn't just gently rippling, it's also bending, folding, and sometimes even tying itself into knots so complex that you half expect to see Einstein rummaging for a pair of cosmic knitting needles. Because here's the truth. The universe loves to tangle things up. Tonight, you drift closer to those twists and warps, peering into one of the strangest possibilities nestled inside Einstein's equations wormholes. Imagine spacetime as a smooth sheet. Then picture someone poking their finger into it, pushing one part closer to another until the fabric touches itself. Voila! A shortcut between distant places. Mainstream fact time. Einstein, along with physicist Nathan Rosen, proposed in 1935 what became known as the Einstein-Rosen-Bridge theoretical tunnel, linking to points in spacetime. It's basically the math version of folding your cosmic map so two dots overlap. Convenient for avoiding long cosmic road trips, but with a few small caveats like possible death by catastrophic collapse if you try to travel through one. Your quirky Einstein tidbit for the night? He sometimes scribbled calculations on scraps of paper, envelopes, even the backs of concert programs when inspiration struck. Physicists still argue whether some of his biggest insights came from moments like these, or whether that's just romantic myth-making we love to tell about geniuses. Either way, keep an eye on your junk mail. You never know when it might become a priceless historical document. Back in your mind's eye, you hover closer to one of these hypothetical wormholes. It looks like a shimmering tunnel, glimmering violet and silver under the starlight. You imagine leaning forward and peeking inwardly to see a different patch of the universe staring back. Galaxies swirl like pearls on black velvet on the other side. And yet, the laws of physics aren't eager to cooperate. The tunnel's walls threaten to pinch shut faster than you could blink. The math suggests it would take something called exotic matter, with negative energy density to prop the wormhole open long enough for anything to pass through. You have to admit, exotic matter sounds like the sort of ingredient you'd see on a sci-fi cocktail menu. One exotic matter martini. Hold the catastrophic spacetime collapse, thanks. Physicists still argue whether wormholes are purely mathematical curiosities, or if they might genuinely exist somewhere in the cosmos. Some believe that quantum fluctuations could spawn fleeting wormholes at tiny scales. Others roll their eyes and insist there's no realistic way to keep them stable for human travel. As debates go, it's somewhere between high-level theoretical physics and the world's most frustrating conversation about the best route through rush hour traffic. Meanwhile, your cosmic perspective widens to observe how spacetime doesn't just tunnel, it also bends light into loops and swirls. This is gravitational lensing, where massive objects like galaxies warp the paths of passing light, creating eerie arcs and rings in the sky. It's a cosmic funhouse mirror, reshaping entire starfields into delicate crescents or double images. You recall Einstein's violin again, maybe whispering in his ear the shapes of gravitational curves. The same equations that predict wormholes also allow massive objects to bend light into these luminous distortions. In 1919, astronomers measured starlight curving around the sun during a solar eclipse, offering dramatic proof of Einstein's theory. The newspapers practically lost their minds. Headlines shouted that Newton had been dethroned. Though to be fair, Newton probably wouldn't have minded too much. He'd already discovered gravity, invented calculus, and gotten bonked on the head by an apple. You drift closer to an Einstein ring, where the perfect alignment of a distant galaxy, a massive cluster in between, and Earth creates a luminous halo. It's beautiful and deeply strange, yet realize you're seeing light that's been bent into a full circle by the warping of spacetime itself. There's a quiet humor in how the universe reveals itself. One moment, it's majestic arcs of light. The next, it's a reminder that our cosmic shortcuts might just be cosmic dead ends. You wonder if somewhere in the math, there's a forgotten equation scribbled by Einstein on the back of a concert program that finally unlocks how to keep a wormhole stable. If so, it's probably still wedged under a stack of old newspapers in his study. As you drift past these cosmic contortions, the notion of spacetime as a simple, smooth sheet feels almost quaint. It's more like an intricate origami sculpture full of folds, hidden flaps, and mysterious tunnels. And you, floating here in your starlit reverie, are beginning to realize that the quiet beauty inside spacetime fabric isn't just about ripples, it's about tangles and twists waiting to be discovered. And hey, speaking of tangles, next time you get frustrated untangling your earbuds, remember, the universe is dealing with wormholes, gravitational lenses, and cosmic knots far worse than your headphone situation. So cut it some slack. Section 4. Still hovering there among cosmic folds and loops, you notice the stars drifting a little differently near the edges of colossal spheres of gravity. It's subtle, like the way a slow waltz lingers in the air after the music stops. And that's when you realize the fabric of spacetime doesn't just ripple or twist. It stretches time itself. Tonight, you're going to feel how time softens and elongates in the presence of mass, as though the universe is taking a long, luxurious exhale. Einstein's general relativity taught us that the stronger gravity becomes, the more it bends not just space but time. Mainstream fact: the clock you keep on your wrist ticks ever so slightly slower when you're closer to a massive object, like Earth's surface, compared to the same clock far out in space. It's tiny nanoseconds difference, but real. GPS satellites even have to correct for this time distortion, so your phone doesn't accidentally navigate you into the ocean instead of the coffee shop. Now for your quirky Einstein tidbit. He was notorious for wearing shoes without socks, because he claimed socks always wore holes. Physicists still argue whether this was a quirky time-saving habit, or a quiet protest against pointless formalities. Either way, it's amusing to imagine him pondering time dilation, with bare ankles peeking out beneath his trousers. So here you are, floating near the event horizon of a black hole, a place where gravity grows so fierce that time itself stretches into near eternity. You gaze back toward the wider universe, and something astonishing happens. Clocks out there appear to spin faster, as though the universe is racing ahead while you drift in a syrupy slow-motion bubble. If you could hover just outside the event horizon and somehow survive the tidal forces that would otherwise turn you into cosmic spaghetti, you'd see stars streaking by at absurd speed while your own heartbeat slows. To an outside observer, you'd appear frozen, caught in a perpetual moment as time nearly halts. Meanwhile, for you, each second would feel utterly normal, just slower. Physicists still argue whether this experience can truly be reconciled across different frames of reference. Does time stop from one viewpoint while continuing for another? Is the slowing purely a mathematical artifact, or is it a real, subjective experience for the traveler? It's the sort of debate that sends scholars pacing corridors at midnight, muttering equations under their breath and probably forgetting their socks. You drift away from the black hole's rim, grateful your atoms remain comfortably unspaghettified, and instead find yourself orbiting Earth, gazing down at glowing city lights. Even here, time is slightly stretched compared to your friends on the surface. Astronauts on the International Space Station actually age just a tiny bit slower, due to both their speed and the slightly weaker gravity up there. It's not much a fraction of a second difference over months, but hey, who doesn't want bonus time? And yet, this gentle stretching of time happens everywhere. Near mountain peaks, time ticks a smidge faster than in valleys. Your brain, of course, doesn't notice these micro differences while you're huffing and puffing up the hiking trail. But the clocks do. Space-time is whispering secrets. Even as you gasp for breath and wish you just stayed home with Netflix, you think back to Einstein fiddling with his violin, maybe pondering how a single sustained note can feel longer or shorter, depending on the tempo around it. Time dilation is like music's rubato, a stretching and compressing of the rhythm, depending on the cosmic gravity conducting the piece. Imagine now a pair of twins staying on Earth, the other flying at near light speed to a distant star and back. When they reunite, the traveling twin is younger than the stay-at-home sibling. It's called the twin paradox, a cosmic prank courtesy of Relativity. Yet another reason why you should always check your frequent flyer miles before committing to interstellar vacations. But here's the beautiful thing. Time dilation doesn't just distort clocks, it hints that time itself is part of the same fabric as space. It's woven into the cosmic cloth, bending and flowing, like silk draped over invisible shapes. You float there, realizing that your own seconds are not absolute. They're not universal. They're yours, and the way they pass depends on where you are and how fast you're moving. Time is personal. Time is flexible. And time, it turns out, is as delicate as spider silk, stretching silently around stars and planets. You wonder whether Einstein, socks or no socks, ever paused mid-equation, closed his eyes, and let himself feel how profoundly strange it is that time isn't a universal drumbeat, but a local melody, unique to every place in space. You like to think he did maybe while gently drawing his violin bow across a trembling string, pondering how the note's length depends on cosmic gravity's hidden hand. So tonight, as you tuck into bed or drift off on your couch, remember, even your dreams are shaped by subtle stretches in the cosmic fabric. The seconds passing in your sleep are not quite the same as those ticking in the vacuum beyond our sky. And if that isn't the perfect excuse to sleep in tomorrow, I don't know what is. Section 5. You've drifted through ripples and bends, past cosmic loops and time's gentle stretching, but now you feel yourself pulled closer, closer still, as though the cosmic fabric itself is beckoning you to peer beneath its weave. You're about to zoom into the tiniest scales imaginable, where the threads of spacetime fray and shimmer, hinting at secrets so profound they might redefine the very notion of fabric. Welcome to the realm of the Planck scale, where distances shrink to about 1035 meters. That's a decimal point followed by 34 zeros and then a 1. It's the tiniest ruler nature seems willing to hand using trying to imagine. It makes your brain sputter like a dying sparkler. Mainstream fact, the Planck length is often thought of as the smallest meaningful scale in the universe. Below it, classical notions of space and time likely lose meaning, dissolving into a frothy sea of quantum uncertainty. It's the scale where quantum mechanics and gravity collide. To theories that, despite their brilliance, refuse to play nicely in the same sandbox. Quirky Einstein tidbit: despite his towering genius, Einstein was never entirely sold on quantum mechanics. He famously grumbled, "God does not play dice with the universe." Physicists still argue whether Einstein's stubborn discomfort with quantum randomness was visionary caution or a blind spot in his genius. Either way, the cosmic dice keep rolling, whether he liked it or not. So here you hover, shrinking smaller and smaller, until entire atoms appear the size of solar systems around you. Dive deeper still, past electrons flickering like anxious fireflies, past quarks bobbing inside protons and neutrons, until you approach the Planck length, and suddenly, the cosmic fabric stops looking smooth. Instead, it fizzes. It's called spacetime foam, a concept introduced by physicist John Wheeler. At scales this small, spacetime might be a roiling, bubbling chaos, with tiny wormholes popping in and out of existence faster than you can say E=mc. It's as if the smooth silk of the universe's fabric unravels into tangled threads, twisting and reconnecting in an eternal quantum dance. Physicists still argue whether this foamy chaos is real or just a mathematical mirage, created by our incomplete understanding of quantum gravity. Some theories suggest it's the foundation for everything we see, matter, energy, even the passage of time. Others believe it's just a convenient placeholder until we figure out a better theory. Either way, it's not the kind of foam you'd want on your cappuccino. Hovering among this froth, you start to wonder, how can spacetime, which seems so serene and continuous at our human scale, become a seething mess when examined closely? It's like discovering your luxurious velvet blanket is made of frayed threads under a microscope. And here's where things get even wilder. Some physicists think the grains of spacetime could be linked to information itself. Imagine the entire cosmos as a gigantic digital file, where reality is built from discrete bits of information woven into the fabric. In this vision, spacetime might not be continuous at all, it could be pixelated like a cosmic video game. You recall Einstein's violin again. Imagine if the cosmic music he played wasn't composed of smooth notes, but of tiny digital pulses. A universe of ones and zeros, strung into a symphony so vast it creates stars, planets, and you. You chuckle, because the idea that reality might be pixelated sounds suspiciously like the plot of a sci-fi blockbuster. Yet here we are, with real scientists exploring whether spacetime has a resolution limit. If true, there'd be a maximum sharpness to reality, a cosmic HD ceiling, beyond which the universe becomes fuzzy. Physicists still argue whether experiments might ever detect this granularity. Could we see diffraction patterns in high-energy cosmic rays that reveal the grain of space itself? Or are we forever stuck behind a veil, unable to probe beneath the cosmic fabric's shimmering surface? It's the cosmic equivalent of wondering whether your favorite video game character knows they're living in pixels, floating deeper. You realize this tiny scale could hold the answers to mysteries that have haunted physics for a century. Why is gravity so weak compared to the other forces? What truly caused the Big Bang? Could wormholes pop in and out of existence, offering shortcuts through spacetime foam? Or would such journeys leave you scrambled like cosmic spaghetti code? You drift in the foamy darkness, half expecting a tiny Einstein to paddle by in a microscopic canoe, muttering about dice and probability. And in this quiet space, it dawns on you, the quiet beauty inside the fabric of spacetime isn't just about its vastness. It's about the mysteries lurking at its smallest scales, whispering secrets in a language we're only beginning to learn. And hey, the next time someone tells you it's the little things that count, remember, they have no idea just how little things can get. Section 6. You're floating now in a hush so deep it almost rings in your ears as silence, stitched from the finest cosmic threads. But into that silence creeps a gentle melody, soft and curious, as though the fabric of spacetime itself were humming. And there it is again in your mind's eye, Einstein, hair unkempt, bow poised over strings, coaxing a delicate tune from his beloved violin. Tonight, you're about to discover how Einstein's music and the universe's own rhythms intertwine, weaving cosmic harmony into the very fabric of existence. Mainstream fact: Einstein was a passionate violinist. He once said, "If I were not a physicist, I would probably be a musician." For him, music wasn't just leisure, it was inspiration, a way to untangle mathematical knots by letting his mind drift on melodic currents. Quirky Einstein tidbit: while he adored playing the violin, Einstein was infamously stubborn about sticking to his own tempo. He'd often speed up during performances, driving his accompanists half mad. Physicists still argue whether that impatience was the spark of genius, or merely the cosmic equivalent of skipping pages in a book, because you can't wait to see how it ends. And you float there, imagining the universe not as silent darkness, but as music, a cosmic orchestra vibrating with hidden notes, because physics has begun whispering something extraordinary, that the tiniest components of reality might not be particles at all, but tiny vibrating strings. Welcome to string theory. Instead of tiny dots, string theory proposes that fundamental building blocks of the universe are minuscule loops, or strands of energy. Each vibrates at a unique frequency, just like the strings of Einstein's violin. The type of vibration determines what the string appears to be: photon, an electron, maybe even a graviton, the elusive particle thought to carry gravity. Physicists still argue whether string theory is the ultimate theory of everything, or an elegant mathematical illusion with no testable evidence. Some see it as our best hope of reconciling gravity and quantum mechanics. Others claim it's like listening to a song whose sheet music looks beautiful, but might never be performed in reality. As you drift closer to those cosmic strings, you picture them quivering in dimensions too small to see, humming frequencies that resonate through the universe's fabric. Each particle becomes a note in a grand cosmic symphony. And suddenly, Einstein's love of music feels perfectly in tune with physics. Maybe he glimpsed, through his melodies, how the universe might be composed of vibration, rhythm, and harmony. You imagine him in his study, violin tucked under his chin, drawing his bow across the strings, each note echoing ideas that might blossom into equations. Perhaps it was during one of those impromptu sonatas that he first felt spacetime bending around mass, like a melody bending around a central note. And yet, the math of string theory can be well monstrous. It requires not 3 dimensions of space, but 10 or even 11 plus time. Extra dimensions curled up so tightly that you'd never notice them. Like violin strings wound so close they appear as a single thread. You float deeper into this concept, pondering how the universe could hide entire dimensions beneath the scale of atoms. It's enough to make your head spin, and yet it's so breathtaking you almost wish you could hear those hidden dimensions singing. Einstein's violin reappears in your imagination, this time not just an instrument, but a metaphor for how the universe plays itself into being. The strings might be cosmic threads, each vibration weaving gravity, electromagnetism, and nuclear forces into a seamless whole. And here's a delightful thought. Physicists still argue whether string theory predicts one universe, or a multiverse of countless realities, each with its own physical laws. It's like imagining an infinite concert hall where every possible cosmic symphony plays out somewhere. In one universe, perhaps you're an intergalactic rock star. In another, you're still struggling to remember where you left your car keys. Back in the quiet cosmic dark, you realize that music and physics share something profound. They're both languages for describing patterns and relationships. Equations and melodies are just different ways to capture the universe's secrets. And as you listen for those hidden vibrations, you wonder if spacetime truly hums with music we simply can't yet hear. Is there a grand cosmic song echoing through the galaxy, waiting for the right instrumenter to play it back? You laugh softly because honestly, if anyone would have insisted that the universe was a musical instrument, it would have been Einstein. Sockless, hair wild, sawing away at his violin in some forgotten corner of the cosmos. So next time you hear a violin's sigh or a cello's low growl, remember you might be catching faint echoes of the very vibrations that weave spacetime into the quiet beauty all around you. And if the universe truly is music, well, you've got front row seats. Section 7. You're still wrapped in the soft echoes of cosmic strings humming their unseen tune, when you sense something else brushing past your awareness, a gentle rustle, like a breeze moving through curtains you can't quite see. Because tonight, we're going to slip into shadowy dimensions that might be hidden tight inside the folds of the cosmic weave. Mainstream fact: one of the wildest implications of modern theoretical physics is that our universe might have more than the familiar 3 dimensions of space and 1 of time. String theory, for example, requires up to 10 or 11 dimensions for the math to work out. But these extra dimensions could be curled up so small that we never notice them, lurking at scales tinier than a proton. Your quirky Einstein tidbit: despite his incredible ability to picture complex geometries, Einstein himself was initially skeptical of extra spatial dimensions. Physicists still argue whether he would have eventually embraced the concept, or whether he'd have politely patted string theorists on the shoulder and said, "Good luck with that, kids." Either way, it's hard not to wonder what he'd think of our cosmic hide-and-seek game today. Floating in the dark, you try to imagine how extra dimensions might exist. Some scientists suggest they could be curled up into tiny geometric shapes, called Calabi-Yau manifolds. Think of these as intricate origami folded so small that they slip beneath the radar of even our most powerful microscopes. Picture spacetime as a vast carpet spread across the cosmos. What if, under that carpet's surface, there were countless little tunnels and chambers, entire geometric cathedrals so minuscule that they escape all detection? You're basically standing on a cosmic shag rug, blissfully unaware that entire universes could be nestled between its fibers. Physicists still argue whether these hidden dimensions might one day reveal themselves through experiments. Could particles suddenly vanish into them? Could gravity's unusual weakness be explained because it leaks into these hidden spaces, while other forces remain trapped in our familiar three-dimensional brain? It's an ongoing debate, like arguing over whether there's an entire hidden apartment inside your closet that you just haven't noticed yet. You think back to Einstein playing his violin, and you wonder if those extra dimensions are like secret harmonic overtones in music notes that exist, but only subtly color the sound unless you're really listening. Maybe the cosmic song we hear is only part of the full symphony. And here's a fun mental image. In some theoretical models, our universe could be a giant membrane, a brain, in physicist speak, floating in a higher dimensional space. Imagine a cosmic trampoline where our entire reality is a two-dimensional surface, undulating through a higher dimensional volume. Other brains might float near parallel universes separated from ours by the tiniest of gaps. A cosmic neighbor might be less than a millimeter away along a hidden axis we can't perceive. Cue the cosmic existential crisis. Is there another you over there, sipping tea and wondering the same thing? And would your alternate self finally have mastered that tricky yoga pose you keep avoiding? You drift closer to a shimmering wall of spacetime, half expecting your hand to slip through into another realm. The extra dimensions might be twisted so tight that nothing can travel through them except maybe gravity, which could seep into those hidden corridors, explaining why it's so much weaker than the other forces. Remember how we've talked about the cosmic fabric bending and rippling? If there really are extra dimensions, every ripple might be more complex than we thought, twisting not just invisible space, but through hidden corridors folded into existence. The quiet beauty inside spacetime fabric grows infinitely richer when you realize the threads might weave through unseen places. Physicists still argue whether evidence for extra dimensions might show up in high-energy particle collisions. Maybe future colliders will smash protons together so hard that tiny echoes of higher dimensional effects will ripple through the debris. Or perhaps those curled-up dimensions will stay hidden forever. Cosmic secrets locked behind doors we don't yet have keys for. Your thoughts spin with possibility as you drift among imagined collabio shapes, their intricate surfaces blooming like crystalline flowers. Each petal could be a hidden dimension, folded so intricately that reality itself shimmers along its edges. And just for fun, you wonder whether Einstein would have pulled out his violin, played a few exploratory notes, and proclaimed the hidden dimensions to be merely another part of the cosmic music, waiting to be heard. So tonight, as you lie there listening to your own quiet breath, remember there might be entire universes folded and atoms width away, wrapped inside the same cosmic cloth that holds you gently in place. And next time you drop your keys and swear they've vanished into another dimension, maybe you're not entirely wrong. Section 8. You're still marveling at hidden dimensions when something darker looms into view. It's like watching silk drawn slowly into a whirlpool, threads vanishing into a perfect, silent circle. And that's when you realize you're drifting dangerously close to one of the universe's most powerful sculpt-torced black hole. Because black holes aren't just monsters that swallow everything in sight. They're silent artisans, warping and shaping the very fabric of space-time with a gravity so intense that even light can't escape. Mainstream fact: a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is a region of space where the curvature becomes so steep that not even light can climb out. That boundary is called the event horizon, one-way door into darkness. Cross it, and no message, no matter how desperately transmitted, can ever return. Your quirky Einstein tidbit: Einstein, despite predicting black holes as mathematical possibilities through his equations, was deeply skeptical they'd exist in nature. He thought nature would find a way to avoid such singularities. Physicists still argue whether he underestimated how weird and ruthless the universe can be, or if he simply couldn't bear the idea of a place where physics itself might break down. Hovering at the edge of a black hole, you feel space stretching like taffy. Time slows dramatically as gravity grows monstrous. To an outside observer, Anything falling into the hole appears to freeze at the horizon, fading away into red-shifted gloom. But for the falling object, say, youth plunge happens in finite time, a terrifying descent into the cosmic abyss. You watch as light curves around the black hole, bending into luminous rings known as the photon sphere. Here, photons circle the black hole endlessly, trapped in an eternal, orbiting limbo. It's beautiful and eerie, an endless cosmic merry-go-round of light. And that's where your mind jumps back to the violin leaning under Einstein's desk. You imagine the photon sphere like a cosmic orchestra pit, with light playing frantic loops around the black hole, its music distorted into lower and lower pitches as gravity stretches each wave. Physicists still argue whether black holes truly destroy all information about the objects they consume. It's called the black hole information paradox. Does information about matter falling and vanish forever? Or does it remain encoded somehow in subtle ripples on the event horizon, a kind of cosmic hologram? The debate keeps theorists awake at night, scrawling equations on whiteboards while their coffee goes cold. Floating closer, you gaze into the black hole's darkness and wonder whether it might conceal a wormhole exit elsewhere in the universe. Some speculative solutions to Einstein's equations allow black holes to connect to white holes, a hypothetical object where matter is expelled instead of sucked in, a cosmic two-way street. Except the math usually suggests any such tunnel would collapse the moment anything tried to pass through. So not exactly a reliable commuting option. The quiet beauty here is deceptive. Black holes may appear like cosmic erasers, swallowing stars and planets whole, but they also sculpt the universe in surprising ways. Supermassive black holes, lurking in galactic centers, help shape galaxies by influencing the motion of billions of stars. Their intense gravity and bursts of radiation can either feed or throttle galaxy formation. And speaking of recent triumphs in 2019, when scientists unveiled the first ever image of a black hole's shadow in galaxy M87, humanity peered into a cosmic abyss and finally saw the silhouette of a phenomenon Einstein once doubted would exist. An image that confirmed, in fiery orange and black, that spacetime truly warps in ways both terrifying and elegant. Hovering there, you sense that black holes are not simply monstrous voids, but silent artists, sculpting the cosmic landscape through gravity's relentless chisel. They carve out regions of space, twist time into spirals, and illuminate the edges of physics where known laws fray into speculation. Physicists still argue whether black holes are the ultimate dead ends or secret gateways to other regions of the universe. Are they cosmic trash compactors, or are they doors to new realms we can't yet imagine? The paradoxes piled around black holes suggest we're missing pieces of the puzzle. And here's a playful thought. Black holes are the universe's strictest bouncers. They'll let light approach the door, but once it crosses the threshold, no re-entry stamp for you. So tonight, as you drift away from the event horizon's deadly embrace, remember, the quiet beauty inside the fabric of spacetime isn't just found in gentle ripples or elegant curves. Sometimes it's hidden in the silent darkness, where even light cannot escape, where spacetime folds in on itself, sculpted by gravity's invisible hands. And if black holes ever become tourist attractions, make sure your travel insurance covers complete annihilation at the event horizon. Section 9. As you drift away from the silent pull of the black hole, space feels calmer again. The stars spread out in graceful constellations, like diamonds spilled on black velvet. And yet even the fabric of spacetime keeps revealing its quiet magic. Because tonight, you're going to trace how light dances through warped spacetime, bending in beautiful, mind-bending ways that reveal hidden beauty in the universe. Mainstream fact: one of Einstein's triumphs was predicting that massive objects bend the path of light. This phenomenon, called gravitational lensing, means that a galaxy's gravity can act like a giant cosmic magnifying glass, distorting and brightening the light from objects far behind it. It's how astronomers now discover distant galaxies otherwise too faint to see, like cosmic paparazzi snapping secret photos from impossible distances. Your quirky Einstein tidbit: despite being hailed as a scientific rock star, Einstein often tried to avoid the press and public attention. He'd sometimes disguise himself by wearing different hats or fake mustaches. Physicists still argue whether this was shyness, privacy, or simply a mischievous sense of humor. Honestly, I'd pay good money for a photo of Einstein lurking behind a lamppost in a Groucho Marx disguise. Back in your cosmic journey, you hover near a distant galaxy cluster. Its mass warps the space around it, creating a distortion that pulls and stretches the images of galaxies behind it into arcs and curves. These glowing streaks in the sky are Einstein rings and arc-stunning evidence that space itself isn't just a stage for light, but a player in the show. Physicists still argue whether gravitational lensing could one day reveal truly exotic things, like clusters of dark matter invisible except for how they bend light, or even the presence of hidden cosmic strings slicing through the cosmos like invisible wires. The idea that we might see something purely by how it bends starlight is the ultimate cosmic detective story. Floating there, you remember how during the 1919 solar eclipse, astronomers observed starlight bending around the sun. This provided one of the first experimental proofs of general relativity, launching Einstein into worldwide fame. Headlines declared him a genius who dethroned Newton, though if Newton were around, he'd probably just give a polite nod and return to inventing calculus or discovering new optical phenomena, because that man was endlessly busy. You drift closer to an Einstein ring, marveling at its perfect circle of light. It's a glowing halo caused when the background galaxy, lensing galaxy, and observer are perfectly aligned. The result is a cosmic bullseye that looks almost too precise to be real. A sign that geometry isn't merely abstract lines on paper, but something the universe wears like jewelry. And then you spot an effect, even subtler microlensing. Here, a single star in a distant galaxy briefly magnifies the light of another star behind it, causing a temporary brightening. It's how scientists have detected exoplanets thousands of light years away. Imagine discovering a new planet because a distant star acted like a cosmic lens. For a few precious hours, the universe sometimes hands you miracles in fleeting sparkles. Einstein's violin pops into your mind again. Gravitational lensing feels like musical echoes bouncing off cathedral walls, notes bending and blending as they travel. The curved paths of photons are like refrains spiraling back to your ears from hidden corners of the cosmic hall. And here's another wonder. Gravitational lensing doesn't just distort light. It can create multiple images of the same distant object. A single quasar might appear duplicated in the sky. Light arriving from slightly different paths bent around massive intervening objects. It's the cosmic version of showing up twice in your own selfie. Physicists still argue whether lensing might one day reveal evidence for fundamentally new physics. Could we glimpse hints of dark matter particles clustering in unexpected ways? Could faint distortions hint at dark energy's true nature? Each distorted arc might carry clues written in light across the universe's fabric. You hover there, letting starlight spill over you, bending into arcs and halos, realizing how the universe constantly plays tricks of perspective. Gravity isn't merely a force, it's the ultimate illusionist, curving reality itself to shape what you see. And as you float through this silent light show, you can't help but grin at the notion that your very sense of sight depends on straight-line photons, while the cosmos insists on bending those paths like a mischievous artist. So tonight, as you blink up at the stars, remember, the starlight you see may have twisted and looped through cosmic valleys, sculpted into arcs by gravity's invisible hand. The quiet beauty inside the fabric of spacetime reveals itself in those graceful bends, in the glowing rings and arcs that whisper of hidden masses and cosmic mysteries. And if you ever get lost while navigating with Google Maps, take comfort knowing even starlight has trouble traveling in a straight line. Section 10. You're floating there, marveling at cosmic arcs and curving starlight, when a shiver seems to pass beneath everything you see, an undercurrent, as though spacetime itself is quietly bubbling just below its smooth surface. Because tonight, we're peeking beneath the cosmic cloth into the frothing mystery known as spacetime foam, a place that nudges closer to Einstein's unfinished dream. Mainstream fact: in the 1950s, physicist John Wheeler proposed that on unimaginably tiny scales about the Planck length spacetime might not be smooth and continuous at all. Instead, it could be frothy and chaotic, with tiny wormholes popping in and out of existence. This roiling chaos is called spacetime foam. Think of it as quantum fizz lurking beneath the calm cosmic ocean. Quirky Einstein tidbit. Einstein spent much of his later life hunting a unified field theory, a single, elegant framework tying gravity, electromagnetism, and perhaps all forces together. He believed nature's laws must fit into a unified puzzle. Physicists still argue whether he was on the right path or if he was stubbornly chasing shadows, while quantum mechanics danced merrily onward without him. Either way, it's a noble quest. Drifting closer. You let your mind zoom back down to those minuscule scales where distances are so small they defy language. Here, space-time doesn't behave like a soft, smooth fabric. Instead, it surges and collapses in unpredictable swirls. Imagine the cosmic silk we've talked about so far, suddenly transforming into a boiling pot of bubbles. Tiny tunnels might constantly flicker in and out of existence. Little pockets of space might momentarily fold back on themselves, creating micro-wormholes no bigger than a proton. Physicists still argue whether these quantum fluctuations are purely theoretical, or might one day be observed indirectly. Some believe the frothiness of spacetime could leave subtle fingerprints in cosmic rays, or gravitational waves. Others think the foam will forever hide behind a quantum curtain. It's the physics version of squinting at static on an old TV set and swearing you see patterns. And speaking of cosmic patterns, you remember Einstein's violin again. Imagine those tiny quantum loops vibrating like trembling strings, each fluctuation part of an ultramicroscopic symphony. Maybe the foam is playing music so rapid and subtle that even the universe itself strains to hear it. You wonder whether spacetime foam might explain why gravity is so weak compared to the other fundamental forces. Could some of gravity's strength leak into those frothy hidden tunnels? Could dark energy's mysterious push also bubble up from this chaotic quantum sea? Floating through this fizzing realm, you see hints of Einstein's lifelong dream. He wanted a theory that united the fabric of spacetime with the forces dancing upon it. Quantum mechanics describes the world as a wild casino of chance, particles appearing and disappearing like magic tricks. Meanwhile, general relativity describes gravity with the calm logic of geometry. Unifying these two views has been physics' ultimate quest for a century. It's the cosmic equivalent of trying to fit a square peg into a round wormhole. Physicists still argue whether string theory might finally bridge this gap. Maybe vibrating strings could smooth out the foam, weaving quantum behavior and gravity into a single elegant melody. Or perhaps the answer lies in new ideas like loop quantum gravity, which suggests space itself might be made of discrete chunks, a cosmic Lego set, clicking together beneath our reality. You drift deeper into the froth, watching spacetime boil and churn. It's as though countless possibilities are vying for existence, each flickering into being before dissolving again. The foam might hide the seeds of entire universe pocket realities blinking in and out, faster than a heartbeat. And yet, from this chaos, the larger universe emerges serene and orderly, like a calm ocean stretching away from a bubbling shoreline. You marvel at how the quiet beauty inside the fabric of spacetime is built atop this roiling cauldron of quantum uncertainty. You chuckle, because the idea that our entire existence floats on a sea of cosmic fizz makes reality feel oddly precarious, like discovering your solid oak dining table is really a seething swarm of subatomic bees. Politely holding hands, you float upward again, leaving the foam behind, and gaze across the galaxy. The stars look serene, but you know now that beneath their glow lies a reality vibrating with untamed energy. And maybe, just maybe, somewhere within that foam lies the missing puzzle piece Einstein searched for, an equation, scrawled on the back of an envelope, waiting to unify everything. So tonight, as you close your eyes, remember, the calm beauty of the universe rests atop a hidden storm. And if your dreams feel a little frothy tonight, well, blame spacetime foam. Section 11. You're still floating upward from the frothy churn of spacetime foam, shaking off the quantum bubbles fizzing in your cosmic hair. And suddenly, the universe seems to hush in a deeper, older way, as if holding its breath, listening to a faint whisper echoing from the beginning of time itself. Because tonight, we're going to listen for the echoes of the beginning, cosmic background whispers woven into the fabric from the Big Bang. Mainstream fact: the cosmic microwave background CMB radiation is the oldest light we can see. It's a faint afterglow left over from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This glow now bathes the entire cosmos at just 2.7 degrees above absolute zero, a soft radio hum, gently washing over the universe. Your quirky Einstein tidbit. Although Einstein's equations laid the groundwork for cosmic expansion, he once introduced a cosmological constant to keep the universe static, because he believed it was eternal and unchanging. Later, he called that his biggest blunder. Physicists still argue whether it really was a blunder or a prescient hint about dark energy. Either way, it's comforting to know that even Einstein sometimes needed cosmic whiteout. Drifting deeper into the night, you imagine space filled with a soft golden Hasieth CMB glowing gently from every direction. It's not visible to your eyes, but if you could tune your radio to the right frequency, you'd hear a faint hiss. Next time your TV shows static, remember, a tiny fraction of that fuzz is the universe whispering to you. From 13.8 billion years ago, physicists still argue whether the faint patterns in the cosmic microwave background hold secrets about the earliest moments of the universe. Did cosmic inflation and explosive expansion in the first split second leave behind subtle fingerprints in these ancient ripples? Or are there clues hidden in the tiny temperature variations, suggesting that our universe might be just one bubble in a vast cosmic multiverse? Hovering there, you gaze at the CMB mop, a swirling quilt of warmer and cooler spots. These fluctuations are tiny, only 1 part in 100,000, but they seeded the growth of galaxies, stars, and ultimately you. The quiet beauty inside the fabric of spacetime is written into these delicate patterns, like musical notes on an invisible score. You recall Einstein's violin once again. Imagine him tracing those CMB ripples with his bow, each variation a faint vibration echoing across cosmic time. Perhaps he'd hear the universe's first breath as a soft, trembling chord. And here's a thought: that ancient glow was once searingly bright. In the newborn universe, the light now known as the CMB blazed at temperatures over 3,000 degrees Kelvin, hot enough to shine like the surface of a star. But as spacetime stretched, that light cooled and redshifted into gentle microwaves, a cosmic lullaby still drifting through your Wi-Fi router's frequencies. Physicists still argue whether the CMB might reveal clues about exotic physics, like primordial gravitational waves, ripples from inflation's violent expansion. In 2014, scientists briefly thought they'd detected these waves imprinted in the CMB's polarization, sparking headlines about smoking gun proof for inflation. But cosmic dust dashed those hopes for now, reminding everyone that in science, the universe often whispers, "Not so fast." Floating in this ancient glow, you realize you're surrounded by a ghost light older than any galaxy. The CMB is like a baby picture of the cosmos, showing the universe before galaxies, before stars, before planets, before coffee shops and cat memes. And yet you're connected to it. The atoms in your body trace back to the same primordial soup that birthed those faint microwaves. You're not separate from the cosmos, you're stitched into its tapestry, your existence vibrating gently alongside the universe's earliest echoes. You drift higher, feeling the faint warmth of that ancient light brushing your cosmic cheeks, knowing that the CMB isn't just background noise, it's a record of everything that has happened since the dawn of time. And here's a playful cosmic joke for you. Next time you're staring into your fridge late at night, remember it glows around 3 degrees above absolute zero, about the same temperature as the cosmic microwave background. Congratulations, you and the cosmos share fridge vibes. So tonight, as you listen for the quiet hum beneath all things, remember, the universe hasn't forgotten its first words. They're still there, woven into the fabric of spacetime. A gentle whisper echoing from the beginning of everything. And maybe, just maybe, if Einstein could hear it, he'd smile, lower his violin, and finally admit the universe is far more musical than even he ever imagined. Section 12. You're hovering there in the hush of ancient starlight, the whispers of the cosmic microwave background fading into silence, and gradually, you begin to sense that this entire journey has been leading you to a place of quiet reflection. Because tonight, we come full circle to your place in spacetime's tapestry, and ponder how your existence is stitched into the cosmic cloth. Mainstream fact: you, sitting or lying there right now, are made of atoms forged in ancient stars. The carbon in your cells, the oxygen in your breath, the iron in your blood were birthed in stellar furnaces billions of years ago. You are literally cosmic dust, gathered into a temporary shape by gravity, chemistry, and a splash of luck. Quirky Einstein tidbit. Einstein once said, "I am enough of an artist to draw freely upon my imagination." Physicists still argue whether his success came from pure mathematical skill, or his uncanny ability to visualize physical reality in ways others couldn't. Either way, he'd probably be delighted to know that you're now imagining yourself as a glittering swirl of stardust floating in the universe's grand dance. So here you are, floating above Earth, watching it spin in its silent waltz through space. The clouds drift lazily across continents. City lights twinkle like neurons firing in a planetary brain. And you realize, you're not just an observer of this cosmic spectacle. You're a participant, a thread in the same fabric we've been exploring all night. Physicists still argue whether consciousness itself might be tied to the structure of spacetime. Are our thoughts emergent properties of neurons alone? Or could the very fabric of reality play a role in shaping awareness? It's the kind of question that hovers at the edge of physics and philosophy, and might never be answered definitively. But it sure keeps people up at night. As you drift there, you think back on all the cosmic wonders you've explored. The cosmic silk of spacetime stretching under Einstein's cluttered desk, gravitational waves rippling like distant harp strings, wormholes tempting you with shortcuts through spacetime, time itself stretching and slowing near massive bodies, the grainy froth of Planck-scale foam shimmering beneath reality's surface, the hidden dimensions curled like origami between the stars, black holes sculpting cosmic landscapes in silent artistry, light bending into elegant arcs and halos, the foamy chaos hiding beneath calm spacetime, ancient echoes whispering from the dawn of time. And finally, this realization, the universe isn't just out there, it's inside you too. You're composed of the same energy, the same particles, the same cosmic laws that govern galaxies and black holes. You're a fleeting arrangement of matter, woven into spacetime's delicate cloth, destined to one day scatter back into starlight. You recall Einstein's violin once more. Maybe the music he played was his way of feeling connected to that cosmic rhythm. Perhaps each note was a way of harmonizing with the quiet beauty hidden in spacetime's fabric of beauty that includes you. And here's a comforting thought. The fabric of spacetime may ripple, stretch, and froth with unfathomable mysteries, but it's also gentle enough to cradle your entire existence. You're small but never insignificant. Your laughter, your sorrows, your quiet moments staring at the starsty all ripple subtly into the fabric, leaving gentle impressions. Physicists still argue whether the universe is ultimately deterministic or random. Are we following cosmic choreography, or dancing our own improvisation across the stage of spacetime? Either way, you're here, and your story is as much a part of the universe as neutron stars or shimmering quasars. So tonight, as you close your eyes, remember, you are floating in a vast cosmic ocean, stitched into a fabric woven by gravity, energy, and the silent music of existence. You're not merely adrift, you're connected, anchored by invisible threads reaching back to the first moments after the Big Bang. And who knows, maybe somewhere, a future traveler will look back at your tiny ripple in spacetime and whisper thanks for the beauty you added to the cosmic tapestry. And if that's not enough reason to keep drifting forward, I don't know what is.